Again, with our notes, really important that you guys always, put your name on there. So I'm going to start just throwing my name on top. And the class period is 3. And then I'm going to put the date on there. And I think the date's really important as well, because if you're studying for a test or something and you have the date down there, you can say, oh, okay, the 17th. For some reason, the 17th I couldn't figure out. So, so you can go back to our class Canvas page and you can look up our video notes, and you can look up my teacher notes to see if maybe you missed something, or you can watch the video again for that particular part and kind of try and figure it out from that. And then always, as always, there's office hours you can come to as well. So just a couple options there to think about for notes. Okay. So we're talking about inverse functions today, and we're specifically linear functions, so straight lines are what we're looking at today. So the first example I have is a table here, and it says original relation x, y, 0, 6, 1, 4, 2, 2, 3, 0, 4, 2, 4, negative 2. Just real quick, can you guys see this, or do I need to zoom in on it a little bit? Just hit me up in the chat if you think I need to zoom in. Give me a thumbs up if you think it's fine. Okay, just so I get an idea from people. All right, looks good, that's good. Okay, so we're gonna roll with this then. If you need me to zoom in, just unmute yourselves, let me know that you'd like me to zoom in. So whenever we're doing an original relation, we have input values, which are the x values. So I'm gonna call that input. And then output values, which is the y values. And for any type of inverse function or inverse relation, all you really need to do is swap the input and output values. So definition of inverse function, we can say interchange input and output values. And what that looks like is if I started with my x values here, 0, 1, 2, 3, 4, and my y values I'll highlight in green, 6, 4, 2, 0, negative 2. What happens down here is I switch them, so now my x values become this green line and my y values become what the blue line was. So I can go ahead and put them in here and say, okay, now my values are 6, 0, 4, 1, 2, 2, 0, 3, negative 2, 4. Whenever we're doing an inverse, we just want to switch the x and y values. So if you notice that I had the green line, that all those y values became the x values of the inverse relation. All the values on the blue line, which were the input values, the x values, became the y values of the inverse. Okay, that's what happens with an inverse function, inverse relation. Okay. So what I need you guys to do next is we're going to look at the graph itself, and we see that I have the point 0, 6. I want to plot the inverse points. So I'm going to actually plot, I'll do this in blue, since we did red for the first points, 6, 0. And then I'm going to plot the point 4, 1. And then 2, 2, 0, 3, and negative 2, 4. And just plotting my inverse points on my graph as well. Okay. All right, so that's the idea for inverses. That's what we're going to be talking about today. Switching the x and y. All right. With a table, I think it's the absolute easiest. With a graph, I don't think it's too bad either. If you have a graph, it might not be a bad idea to write out a table and then switch the x and y. values. I think that's kind of an easy way to do it. We'll talk about that a little bit more as we go. But let's start with the first example I have here. It says find an equation of the inverse for the inverse of the relation y equals 3x plus 12. Another way we might see this written sometimes, we might see it written as f of x equals 3x plus 12. And all the f of x equals 3x plus 12 is a function notation. So I'm going to write that down here. So that's what function notation looks like, which sometimes on your homework you might be dealing with a function notation problem. And the steps for finding an inverse, if we're doing it from an equation, first we're going to swap x and y. I'm going to put that in quotations because it's just our inputs and outputs. The variables might not always be x and y. It might be d and t. It might be a and b. All right, but you're going to swap your variables, okay, whatever they are. And if your equation's written in function notation, I'll start with this one, 3x plus 12. The first thing I would say to do is rewrite it as a y equals instead. And then this is what the equation was, y equals 3x plus 12. When I swap x and y, I'm going to get x equals 3y plus 12. That's what swapping x and y looks like. So I get x equals 3y plus 12 instead. And then the second part is to solve. I'm going to zoom in a little bit here. So now I have this new equation, x equals 3y plus 12. I'm going to solve specifically for y. So I just need to get y by itself. And it's a simple algebraic equation at this point. I'm going to divide both sides by 12. Or not divide, I'm going to subtract both sides, 12 from both sides. I'm going to get x minus 12 equals 3y. And then I'm going to divide both sides by 3 because I have 3 times y. So I need to divide both sides by 3. And I'm going to end up with something that looks like y equals x minus 12 over 3. Okay, that's what today's lesson is about. Can we do that with an equation as well? So can we do it with a graph? Can we do it with a table? Can we do it with an equation? Those are the three things we're focusing on today. Because I have y equals, another way I could write this, technically, this isn't simplified all the way with the x minus 12. I could rewrite it as 1/3 x, oops, I don't need the, sorry, I don't need the parentheses there. It's going to be 1/3 x minus 4. And that's if I divided both numbers individually by 3. Okay. So that's the way I'd write it if it was the most simplified. The intermediate step, I guess, would be 1/3 parentheses x minus 12. Let's write that actually first. Sorry. So if I did this, 1/3 times x minus 12, and then distributed that, I would end up with 1/3 x minus 4. That might make it a little more clear where I got that 4 from. Okay, because it'd be x divided by 3 and 12 divided by 3, which is 4. All right, so that's where these solving problems comes from. One more quick note here. I have a note over here, this f minus 1 symbol, and what that is if I take our answer here, I could technically rewrite this as f inverse of x equals x minus 12 over 3. So this is our example of inverse function notation. And there's a little note on the right-hand side of the paper that says that the symbol -1 is not an exponent. All right, it's just symbolic. It's just saying this is how we write f inverse, is with this f to the -1 power looking thing. So it looks like it might be an exponent, but it's not really an exponent. That's kind of what that's saying there. Okay. Okay, so we're going to move on. Are there any questions so far on just the solving part? Okay, great. Next part we're going to do then is we're going to look at a graph and how to graph inverses. Woo. Zooming out a little bit. Wants to rotate on me. So when we're graphing, I'm going to go ahead and look at my graph on the left-hand side here, and I'm going to find some points. So like I see a -6 there, -5, -4, -3, -2, -1, 0. So those look like some good points I can use. And what I should do first, I think that's maybe easiest, because I'm going to swap the x and y values again, just like I did on the previous problem. Not x plus y, sorry, x and y. So I can create a table for myself here. And I think that's going to be the easiest way to keep track of all of my values when I do the swap. You don't have to do a table, but for me, I kind of like doing that. Okay, so I'm going to zoom in on my table just a little bit. I saw the first value on the left side was -6, -6. The next value was -5, -3. And then I had -4, -0. -3, -3. -2, 6. 1, 9. And then finally, I ran out of space. My last one was 0, 12. So I create this whole table of values. And if I want to do an inverse, then I just swap the x and y's. So I can call this one right here my original. And then down here, this was my, I'll do another table, it's just the inverse. And write down the swapped values. So do a quick inverse drawing. Make sure I include enough columns this time. All right, and then my swapped values now. Well, the first one's going to be -6, -6 again. And I can just write my entire y column across on the x values. -6, -3, 0, 3, 6, 9, 12. And then I can take my entire y column and write across. Okay. And then the last step, I'm going to plot my new points over here on the left side. So you know what I'm going to do? I'm going to just delete those real quick, and I'm going to change the color, just so we can plot them in a different color on the finished paper. Oh yeah, and I see that I have a mistake up here. This should be -1. All right, so now I'm going to plot these green points on my graph. That's the last step. -6, -6. And then I have -3, -5. So -1, 2, 3, -5. 0, -4. And then I have 3, -3. 6, -2. 9, -1. 12, 0. And my last step would be to sketch that line through those points. Since there's a line shown on the original function, I want to sketch a line for this one as well. And if I'm a good student, I'll draw arrows on my graph showing that this line goes on forever in both directions. And the last thing I'd want to do, because there was an existing line on there and now there's two lines on here, I'm going to label them. So there's my original function, f of x. I'm going to label that in blue. I'm going to label my inverse in green here, f inverse of x. All right. Any questions so far on that part right there? Okay. The last thing I want to mention real quick before we move on, there's a note on the start of page 2 that says the graph of an inverse relation is a reflection of the original relation, and the line of reflection is y equals x. So I'm gonna highlight that real quick. Yeah, there's the line of reflection, y equals x, and it's going to reflect over that line. That means whenever we're taking a function and we're finding its inverse, we're going to see a reflection over that line. And if I were to sketch that line here, I'm just going to do dashed lines. There we go. We'll see that that line does create a perfect mirror. We've talked about reflections last year, maybe over the x-axis, over the y-axis. But an inverse is going to have its reflection over that diagonal line, y equals x, which is kind of weird. But that's going to happen with any inverse function. You'll see that type of reflection. Okay, I've got 4 problems here. I want you guys to work on these 4 problems. Take a couple minutes. I'm going to put the answers up, and feel free to ask questions if you get stuck on something. You can hit me up on the private chat if you don't want to ask out loud. If you don't mind asking out loud, go ahead and unmute yourself and ask. But work on problems 1 through 4 now. Just take a few minutes to do that. Okay? And I'll put the answers up in a minute here. All right, so for problem 2, we're just plotting the points. We're not going to be drawing any lines or anything like that. And I did each one in a different color. So you see I used blue to represent the original point, -1, 2. And the inverse point is 2, -1. I used yellow to represent a point. The original point was 4, -2, so its inverse is -2, 4. All right, that's kind of how those problems work. Problem 3, those are my favorite ones. Switch the table, love it, love it, love it, love it. Problem 4, I just wrote the answer. I did not show my work. Does anyone have any questions on any of these 4, or is there anyone that wants to see the work on problem 4? Just hit me up on the chat or raise your hand, whatever works best for you, if you want to see the work on problem 4. Okay, so we do want to see the work for problem 4, not a problem. That one's a tricky one because of the fraction. So let me go ahead and show you this one. We'll start with first thing we're going to do, I have the instructions written next to problem 1. Rewrite it. So I'm going to rewrite that g of x, which is in function notation, as y equals instead. Second step is to swap x and y. And then third step is going to be go ahead and solve. So I'm going to start by subtracting 3 from both sides of the equation. And I have this -1/2 times y. And what happens there with -1/2, that's realistically, that's just, you would say I'm going to divide by -1/2, which is weird because you're dividing by a fraction by another fraction. That's kind of a weird way to do it. The best way to think about it instead is multiply by the reciprocal of that fraction. And the reciprocal, you might remember that word, you might you might be like, oh, I've heard that word before, I don't remember what it means. It really means multiply by both sides by the fraction flipped over. So negative 2 over 1 times x minus 3. Or negative 2 over 1 times negative 1/2 x, or y. Sorry, that wants to be y. That's what we would be doing for a reciprocal. So in this case then, I get negative 2 times x, that's negative 2x. Negative 2 times negative 3 is positive 6. And then I have negative 2 over 1 times negative 1/2. That just becomes a 1. So I get y equals negative 2x plus 6. I might have skipped a couple steps there. I hope that wasn't too terribly confusing. But that's the idea for problem 4 there. Okay, any other questions on these 4 before we move on? And remember, if you just want to ask me privately something, you can always hit me up on the private chat. That's perfectly fine too. Okay. All right, so we're all good. Last thing we want to talk about today, domain and range. So last thing. Scroll us down a little bit. Domain and range, that's basically, it's a mapping is what we would call it. So yeah, I'll just do blue. Now I'll do red. So it is mapping or pairing is another way we can call it, of input values with output values. And what that really means, domain and range, is if I give you an input value, like an x value, I say, hey, the x value is 3. What's the y value or values? What are the y values that correspond to that input value? That's what domain and range is. It's trying to figure out where those values go together. All right. So we're going to talk about domain and range specifically in what's called interval notation here. That's what I'm going to use today. Okay. Domain's going to be either the input values, which is like the x values, or the y values. Does anyone remember? Is domain the x values or the y values? What do you think? Is domain going to be the x values or the y values?
X.
It is the x values. Very good. That's what I'm looking for. So domain is actually going to be the list of all possible x values. And the range is the list of all possible y values. And what that really means is, like, what x values make this equation work? Or what y values make this equation work? So the example I have here is f of x equals 2x minus 1. So if I'm looking at, I'll just go back up a little bit. I'm going to come back down, don't worry. But I see this line here, a straight line on this graph that I have the blue f of x there. And that line's going on forever in both directions. So theoretically, it doesn't matter what I plug in for x. Like I could plug in negative 10 for x, and the line's going to intersect negative 10 eventually down here somewhere. I just don't see it on my graph exactly. So pretty much any value works for x. That's what's happening there, okay? So that's how domain works. And with linear functions, the domain is actually really easy because it's always, always, always going to be all real numbers. So when I'm writing domain, I'm just do capital D like that. That represents domain. And when I'm writing range, I'm going to do a capital R like that. That represents our range. And yeah, like I said, domain's always going to be all real numbers. If we're doing interval notation, we're going to do like this parentheses, and we're going to go from negative infinity to positive infinity. And for range, we're going to go the same thing, all real numbers. Every x value is going to have exactly one y value. So also negative infinity to positive infinity. That would be our domain and our range for any linear function. So if I ever ask you an assessment or something, hey, what's the domain of this linear function, this straight line? You can always say all real numbers. What's the range of this straight line? It should always be all real numbers, unless there's a hole in the line or something like that. But typically we just have straight lines that go on forever. And that's domain and range. Any questions on that? Okay, great.